Okay, everybody, welcome back. This is going to be some help on the homework problems for homework 6-4 and 6-4, and we're going to start with number 4. All right, and this might just be one problem. I'll probably save other problems for separate videos, but this is going to be number 4, and this deals with an astronaut inside of a rocket. Okay, so let's go ahead and draw our rocket, and I'm going to make it big enough that I can actually draw an astronaut inside of it. So there's a rocket right there. Okay, it's blasting off, and I'm going to make a floor right there for inside the rocket for the astronaut to stand on. And here's our astronaut. Okay, inside of the rocket. So what do we know about this this astronaut? Well, first of all, let's write down all of our knowns. Okay, so the mass of the astronaut is 92 kilograms. Okay, 92 kilograms. And the acceleration, we might say the acceleration of that whole system, right? Very much like maybe a person inside of an elevator. The acceleration of the whole system is not free falling, right? No, it's actually moving upwards. And so we can say the acceleration of the whole system is 30.5 meters per second squared. As rockets tend to do, they move upwards. They actually move up against gravity, so that's why that's not negative. So you can't assume the acceleration is g, or 9.81. No, the rocket doing what it's supposed to do is accelerating the astronaut upwards. So that's the acceleration of the whole system. The rocket's accelerating that at that rate, and so is the astronaut, because the astronaut is part of the system in that rocket right there. Okay? So the question is, what is the apparent weight of the astronaut? All right? Or you might say, what is the supporting force of that astronaut? Because after all, if he's inside of a rocket and he wants to weigh himself to see how much he weighs when the rocket is accelerating, what's he going to do? Well, he's probably going to stand on some kind of a scale, right? There's a scale right there. All right, that scale is supporting him and therefore is presenting with him a readout of how much force it is supporting him with. Okay, so that supporting force is going to be part of the forces that are acting on him. All right, I'm going to finish coloring that in a little bit right there. So let's start by solving for that apparent weight or supporting force by writing a statement about the net force on the system. Okay, let's start with the whole system net force. The net force in the whole system is equal to the mass of the whole system times the acceleration of the system. In fact, mass of the system times acceleration of the system. All right. Even though there's a rocket involved, the rocket is really just providing the supporting force. So we don't the mass of the rocket doesn't really matter. It's really just the astronaut right here, right? He's the whole system that is his mass is being accelerated. Okay. And we know the acceleration of the system because the astronaut and everything about him is moving at that rate. 30.5 meters per second squared. Okay? So that is you might say, a blanket statement of the whole, of the net force on that whole system. Mass of the system times the acceleration of the system. But we try to write this we can write this two different ways. We can write this also as a statement about the net force being you might say, the sum of all the component forces that are acting on him. All right? So that brings us to, well, what are those component forces that are acting on him? All right, let's go back to the astronaut here. First of all, what force is acting on him because he has mass? All right, well, if he's blasting off from Earth, all right, Earth still has gravity as you go, even as you go up. You know that if you stand in an airplane, there's still gravity in an airplane, right? Just because you're off Earth's surface doesn't mean you have less gravity. So he still has his weight force. I'm going to draw him as a point mass right there, acting downwards. All right, his normal weight, mg. This is always true. All right, always has mg acting downwards. Always, always, always. But the scale might read something different, right? Because even though he has a weight that is on the ground of mg, the scale might be providing a greater supporting force. Well, or lesser supporting force, right? You know that if you're in an elevator, your apparent weight or the supporting force changes depending on if the elevator is going up and down, right? That's what we're actually solving for right there. This apparent weight, this supporting force. So we can say that the sum of all the forces on this astronaut is this force, the supporting force that the rocket is applying, or the floor of the rocket is applying to him that has a scale on it, versus the downward force caused by gravity acting on his mass, right there. Okay? So as we tend to do, we're going to be treating downwards as minus and upwards as plus. So let's write a statement now for all the component forces acting on him. There's only two forces, and remember, net force is the sum of all the forces, or if some are negative, you're going to have the difference of some of the forces, all right? Well, what force do we have acting on him? Well, the positive force is the supporting force, or his weight, or his apparent weight, right? That's acting upwards. What's acting downwards is his weight caused by the acceleration of gravity, mg, right there. This is always going to happen, all right? But this might be a different supporting force depending on what the system is, depending on the acceleration of the whole system. All right, so we have stated net force two different ways. We've stated it as a system statement and also as a individual component statement. We've like itemized all the components. This acting up, this one acting down. And we made a statement about them right there. So, since these are both statements about the exact same thing, net force, we can say, hey, these are equal to each other, and we can solve for what we don't know. We're solving for the supporting force, right? We're solving for this right there. So let's write everything all out. Mass of the system, or really just mass of the astronaut, times the acceleration of the system, my S's aren't coming out right, equals the supporting force, or the weight force, or FW, or you might call it the apparent weight. All those are kind of ways of thinking of the supporting force, minus the downward force that is being caused by gravity pulling him down. Okay? So these two statements are equal, therefore we can say that is equal to that. Well, we're solving for this right here. So let's just go ahead and move some things around. So we can say the supporting force is going to be equal to mass of the system, that is the astronaut, times the acceleration of the system, plus mg. All right, now if you think about that for a second, the force, you've got this force plus this force. All right, well, he's moving upwards. If you think about it, if you move upwards in an elevator, if an elevator is accelerating you upwards, don't you feel heavier? Don't you feel that there's more weight between your feet and the floor? So let's plug everything in and see how much he actually weighs because of the whole system accelerating upwards. All right. Mass of the system, so the mass of this guy is 92 kilograms, times how much is that whole system accelerating? 30.5 meters per second squared. All right. Oh, you might have heard a bell in the background right there. We'll try to finish this up. Plus, what's the m? Well, that's 92 kilograms again, right? Times g, 9.81 meters per second squared. If we do all of our math, the supporting force comes out to about 3,700 newtons, which, well, the answer says 3.7 kilonewtons, but that means the same thing. All right, so that's how much he weighs in that spaceship right there, in that rocket. It's a lot more than he weighs at rest. But because that system is accelerating upwards, it creates an extra supporting force that has to support him, otherwise he'd fall through the floor. All right, so this is his apparent weight. You can think of it as weight apparent. Same thing as the supporting force that the astronaut experiences. I hope that helps. I'll see you on the next problem.